discussion. This is part 3 of the series, Water Fiber Reinforced Polymer Composites. In the last discussion, we were talking about the modulus. The modulus of a composite. I was discussing the unidirectional case. So let this block represent a unidirectional composite material. Unidirectional meaning that the fibers are lined up in one direction. The modulus of this composite is given by the expression modulus of composite is equal to modulus of matrix times the volume fraction of the matrix plus the modulus of the fibers times the volume fraction of the fibers. It's very convenient to express it in this other form here in terms of writing Vm in terms of Vf, and of course Vm is the volume fraction of the matrix, and it's related to the volume fraction of the fiber because in a composite that is made of only two constituents, the volume fraction of one component is determined by subtracting the other component from the whole. So the modulus of the volume fraction of the fiber is equal to 100% of the composite, of the volume fraction of the composite minus the volume fraction of the fiber. So if you want to obtain the volume fraction of one, simply subtract the volume fraction of the other from the whole, which is why it's easy to rewrite it like this. So modulus of the matrix is given by 1 minus the volume fraction of the fiber plus modulus of the fiber times the volume fraction of the fiber. I'm sure this is clear enough. Vm is equal to 1 minus Vf is what I was explaining. Okay, so this applies to the unidirectional case, as I said. There are ways to, and by the way, we're talking about the modulus in this direction, the stiffness in this direction. There is another way, there's a way to calculate the stiffness in this direction. Well, right now I'm going to calculate this. There are also much more advanced calculations that we'll be doing on modulus, where we'll even be talking about the stiffness matrix and the compliance matrix, we'll get it, but this is step 1. So a quick example, just to show how this is used. Let's assume that these fibers are made of carbon. These are carbon fibers, okay? Carbon fibers. And specifically, let's assume they are the type made from the polyacrylonitrile precursor. Okay? And that has a modulus of 270 GPa, thereabout. So the modulus of the fiber, and then let's assume that that composite is made of a matrix of epoxy, and let's assume the epoxy has a modulus of 3.7 gigapascals. And then a volume fraction, let's assume a volume fraction of 60%. So 60% by volume of fibers making up the overall matrix. So that means Vf equals 60%, which is also the same thing as 0.6. Then we can calculate the modulus of the composite using this expression that we've just put up by basically multiplying the modulus, that's EF, so 3.7 GPa times 1 minus VF is 0.4, okay? So 1 minus 0.6 is 0.4 plus 270 times 0.6. So this comes down to 108. This comes down to 1.48. So the modulus E composite is equal to 1.48 plus 108, which is 109.48 gigapascals. Okay. So these numbers illustrate a point, and that point is the idea of reinforcement. We have a starting polymer, epoxy, with a modulus of only 3.7 GPa. So the idea of reinforcing it, we're trying to make it, give it better mechanical properties by introducing a material with a much higher value. Okay, whether it is stiffness, and this is a very similar calculation for the tensile strength as well that is done. Very similar expression, similar rule of mixtures approach, and I'll do an example to illustrate that. These are the simple building blocks, because we're going to go into much more advanced concepts as we move along. So the idea of reinforcement is very clearly underlined here in this example. Low stiffness material, which serves as a binder holding the fibers together, protecting them from the elements, holding them in their mean positions, and a high stiffness material. This could very well be tensile strength, but let's talk about stiffness now. We'll illustrate the tensile strength later on. So you look at the numbers, 270 gigapascals, adding it to a material with a modulus of 3.7 gigapascals, and arriving at a composite with a 60% volume fraction for the fiber, a composite with a modulus of 109.48, which is a vast improvement over the 3.7 GPa material. Okay, so we started with essentially a material that had low properties, mechanical properties, and we added another material, and now here we go. We have something really much better than where we were in the beginning, 109.48 gigapascals. So this is a very clear illustration of the idea, and obviously I mentioned in the previous discussion that we were looking at this from the perspective of mechanical properties. And as I said, there are composites that can be made for to exploit thermal properties. So you can make them to exploit electrical properties. There are many reasons why you would want to make them, but this is a mechanical property oriented approach to fiber reinforced polymer composites and composites in general. We will have put up other examples, and I'll discuss stiffness next. So to underline, just before I end this video, and I was told that shorter videos are more helpful to make concepts more digestible, so this is a much shorter video than you're going to see in the previous on the list. But basically, the volume fraction is an important idea. It's very important. If we change this volume fraction now of 60%, let's say in lieu of 60% we had 10% of fiber. From this expression you can already imagine that this number would be a lot lower. And if we manage to squeeze in a higher percentage, let's say 90%, of course our modulus would be closer to 270 GPa. But it's a balance. If you put too much. By the way, there are practical reasons, and I'm going to talk about this in detail. Okay, there are practical reasons why you cannot pack too much. You cannot pack fibers in beyond a particular percentage point because of geometric reasons. These fibers occupy space in a particular shape. If they are made of, if these are cylindrical fibers, there are packing efficiency issues that come with stacking cylindrical materials together. When you arrange a bunch of cylinders, you're going to see gaps between them. Let's imagine from the cross-sectional view, stacked cylinders, and we'll look at what the practical considerations are. So you can see the space there looks like this. And you can see there's a gap there, So the unidirectional case is the case that allows you to have the highest packing efficiency. But this is not the way that composites are generally laminated, because there is a concentration of strength in one direction, or stiffness, whichever property you're looking at, in one direction, but it's relatively weak in this other direction. So plies are usually placed on top of one another, oriented at different angles, in order to create a composite that has more homogeneous properties in multiple directions. But yeah, that's that's the concept really.